Hello, let us continue our discussion on black body radiation. So we know the energy density in the dimensionless form. U dash of x dx is equal to x cube dx by e raised to x minus 1. And this is the Planck's formula, Planck's law. And we have if x is very much less than 1, then u dash of x is equal to x square. So this is the Rayleigh Jeans formula. And also we have when x is greater than 1, very much greater than 1, then this quantity u dash of x is equal to x cube e raised to minus x. Okay, so this is the Jeans law. Okay, so we have seen this thing and we have plotted the graph. So I'll draw the graph once more. So these are the graphs for the corresponding laws. Rayleigh Jeans formula it is at a low frequency. Rayleigh Jeans formula is in agreement with the Planck's radiation formula, and Wien's law is in agreement with the Planck's formula when x is very much greater than 1. Okay. So anyhow, the area under this curve, area under the curve, area under the Planck's curve is so we can get this. So it is equal to integral u dash of x dx is equal to integral x cube dx e raised to x minus 1. Okay, from 0 to infinity. If you integrate from 0 to infinity, you will get this thing. So here we know g Bose-Einstein function g nu of z is equal to 1 by gamma of nu integral x raised to nu minus 1 divided by z raised to minus 1 e raised to x minus 1 dx. So if in this case, in our case, mu is equal to 0, therefore z is equal to 1. So we can write this thing as so this thing as z is equal to 1, therefore we can write this is x cube by dx, so e raised to x minus 1. So we can write this thing as g4 of z is equal to g4 of 1, z is 1 into gamma of 4, gamma of 4. Okay, g4 of 1 is z plus z square by 2 raised to 4 plus z cube by 3 raised to 4 plus etc. So this is nothing but zeta Riemann function of 4. Okay, zeta function. Okay, so g4 is, therefore we can write this integral as zeta of 4 into f4, that is 3 factorial. Yeah, sorry, gamma of 4, that is 3 factorial. Therefore we can write this. What is this thing? This value converges to pi raised to 4 divided by 90. Okay, so we can write this thing as this integral as pi raised to 4 divided by 15. Okay, so this is the area under the curve. This is approximately equal to 6.49. This is equal to 6.4. So the area under the curve, that is integral u dash of x dx in the Planck's case. Okay, Planck's. In the case of Wien's law, in the case of Wien's curve, so this is integral x, integral u dash of x dx is equal to integral x cube e raised to minus x dx 0 to infinity. So this is equal to, this is nothing but gamma function of 4. Okay, this is gamma of 4, which is equal to 3 factorial. So this is 3 factorial 6. So it's equal to 6. So this is approximately 6.49. This is 6. So it is very clear from this graph that so the area of this area under this curve is slightly greater than the area under the second Wien's curve. Okay. So that is obvious from this result. And the area under the curve is, see, the Rayleigh-Jeans curve, however, suffers from a high frequency catastrophe. So we are not taking the area. It suffers, it deviates from this curve. So it goes to infinity as x tends to infinity. Now the energy density, the total energy density of the cavity, that is equal to, that is given by U divided by V, is equal to integral U of x dx. So U of x dx is the energy density as a function of the dimensionless quantity x. X is equal to h cross omega divided by kt. Okay. So from 0 to infinity. So for all the frequencies, all the value of x. So this is equal to what is u of x? U of x is equal to kt raised to kt whole raised to 4 divided by pi square h cross cube c cube. We have derived it into integral u of x is kt raised to 4 pi square h cross cube c cube into x raised to 3 divided by e raised to x minus 1. So integral of this thing will be this into integral x cube x divided by e raised to x minus 1. Okay, from x from 0 to infinity. So this is equal to, so if you integrate this thing, this integral result will be pi raised to 4 by 15. So this is equal to pi square kt raised to 4 divided by t raised to 4 divided by, so this pi square 15 h cross cube c cube. So this is the energy density, or energy, total energy divided by the volume of the cavity. Now if there is a small opening in the cavity wall, if there is, so that there is a cavity and we have calculated the total energy or total energy per unit volume. So if you have a small opening here, then the energy inside, the photons will come out. Okay, the photons will effuse through the this opening. So the total radiant energy per the radiant energy per unit time per unit area. Okay, so that is given by, this is given by E equal to 1 by 4 U divided by V into C. So this is the rate of rate of flow of radiation per unit area, or radiant energy per unit time per unit area. So from this, so this we have derived in the chapter, third chapter, I think so. So this is equal to 1 by 4 u by v is this value. So this is equal to into c. So this is equal to pi square kt whole raised to 4 divided by 60 h raised to h cross cube c square. Okay. So this is the radiant energy per unit area per unit time. So this is can be written as sigma into t raised to 4, where sigma is equal to pi square kt, sorry, pi square k raised to 4 divided by 60 h cross cube c cube. Okay, so all these are constants. So this is called another constant. This is called a Stefan's constant. Stefan constant. Okay. So if you substitute the value of these are universal constants. If you substitute the value of all these things, you will get 5.67 into 10 raised to minus 8. The unit is watt per energy per unit time. So that is watt per meter square. This is the energy per unit time per unit area. T raised to 4. So it is Kelvin raised to minus 4. Okay. So this is the Stefan constant. And this law is called Stefan-Boltzmann law. Stefan-Boltzmann law. Okay. So Stefan experimentally found that this energy per unit area per unit time through from a black body is proportional to the fourth power of the absolute temperature. Okay. And Boltzmann derived this through his thermodynamic derived the thermodynamics of this. Okay. And the next thing is we wanted to again further proceed the thermodynamics. So we have equation of state PV by KT is equal to, we know PV by KT is equal to the Q potential, or which is equal to log grand partition function. Okay. So for this photon gas, this is equal to, since this is Bose-Einstein, so summation minus summation log 1 minus z raised to z e raised to minus z is 1, so therefore z is equal to 1, so e raised to minus e divided by kt. So this is the value of this is the quantity PV divided by KT. Okay. Now the summation can be replaced by, see, this is photon gas, so large number of photons are there, so summation can be replaced by integration. Therefore we have to multiply with a factor, that is PV divided by KT is equal to minus integral log of 1 minus e raised to minus e divided by kt into a of e d. So a of e is the number of total number of phase points, okay, microstates. So we have to, or total number of we can say that yeah, we can say the total number of microstates. We know already what is this quantity. So this is equal to integral log 1 minus e raised to minus e by kt. A of e, what is A of e? A of e is equal to, we actually 2 times v 4 pi p square dp. Okay, a of e dE is equal to 2 times volume to 4 pi p square dp by h cube. This 2 is because the photon has multiplicity 2. So that means horizontal and vertical polarization. So we have to multiply the total number by 2. So we can substitute. So what is P? So using a relativistic consideration, extremely relativistic energy. So this is the momentum is equal to E divided by C. Momentum is not. So for ideal gas case, we have seen that momentum is equal to root of 2me. So this is not the case in this case of photon. Okay, photon is massless particle. So photon momentum is energy divided by the velocity of light. Okay, or h nu by c. So we can write both. So if we substitute here, then A of EDE will be equal to D is equal to 8 pi V H cube divided by H cube divided by H cube. Sorry, let me put this as 8 pi V divided by H cube E cube divided by C cube dE. Sorry, E square D. E square dE divided by C cube. That's it. So we can substitute here 8 pi V divided by H cube C cube E square dE. Okay. Now using this thing, we can write minus 8 pi V divided by H cube C cube. Integrating this thing, log 1 minus e raised to minus e divided by kt e square d from 0 to infinity. So this can be written as, you can integrate this thing with by parts, that is 8 pi v divided by h cube c cube integral minus is there, integral log of this thing, log 1 minus e raised to minus e by kt e square dE. So this will be first term log 1 minus e raised to minus e divided by kt into integral of second term. So e raised to 3 divided by 3 from 0 to infinity minus integral of differential of first term. Differential of first term means 1 divided by 1 minus e raised to minus e divided by kt into differential of the bracket term. So 1 minus, so this will be minus e raised to minus e divided by kt into minus 1 divided by kt. Okay, into integral of the second term e raised to 3 divided by 3 dE. Okay, so this integration, so therefore we'll get So when we put infinity, e raised to minus infinity, so this will become 0. So 1 minus 0, 1. Log 1 is 0, so this term will be 0. When we put 0 here, this because of this e cube, then 0 cube it will be 0. So therefore this is legally 0. This term is 0. The first, therefore we will get minus, here minus is there, so minus minus or plus. So finally the final expression would be, so this is equal to this thing. Therefore we can write, we can also, we can put now this, what is this quantity? This quantity is PV by KT. Okay, so this is PV divided by KT. Okay, now we can put, for simplification we can put this E divided by KT is equal to X. Therefore E is equal to KT times X. DE is equal to KT dx. Okay, so substituting this here, we will get PV is equal to this KT cancel. Therefore PV is equal to 8 pi V divided by 3h cube c cube into integral e raised to minus x. So first we can put this e raised to minus x. So this will e raised to minus x divided by 1 minus e raised to minus x into e cube. E cube is kt cube x cube. Then d is equal to kt dx. Okay, so this thing can be written as, so we can divide this numerator and denominator by e raised to minus x. Then this will be 8 pi v kt raised to 4 divided by 3 h cube c cube integral x cube dx divided by e raised to x minus 1. Okay, so this integral we have already obtained. We obtained this integral as pi raised to 4 by 15. Okay, so therefore we will get PV is equal to 8 pi raised to 4, sorry, pi raised to 5 v k raised to 4 t raised to 4 divided by 15 into 3, 45 h cube c cube. Okay, so this is PV. So but we have similar kind of expression we got for, we have for the energy density, isn't it? Okay, okay, yeah, we got some other expression. So energy density U by V, but we have, energy density is equal to pi square k raised to 4 t raised to 4 divided by 15 h cross cube c cube. We derived it already. So when you replace h cross divided by h by 2 pi, so then it will be 8 pi raised to 5 k raised to 4 t raised to 4 divided by 15, sorry, 15 is 15 h cube C cube. So this is U by V. Therefore, U is equal to 8 raised to 5 V divided by 15 H cross cube C cube. Okay, sorry, not H cube divided by C cube. Okay, so we have PV is equal to 8 pi V K raised to 4 T raised to 4 divided by 45 H cube C cube. Here this thing is one third of PV is one third of, actually PV is equal to one third of the energy, okay, internal energy of the total energy of the cavity. Okay, so this is so the pressure of the radiation is equal to one third of the energy density of the cavity. So this is the expression for radiation pressure. So we have derived the relation between so this is the expression for radiation pressure. We have derived radiation pressure. Okay. So this is very important as a question. It may be, it is very important for many examinations also. So we should study this well, very good. Okay. Next is so energy density we discussed. Now next thermodynamics, we continue again with the remaining thermodynamics. So we have mu is equal to 0 for photons, okay, or radiation photons, okay. So therefore, and z is equal to 1, therefore, okay. Therefore, we can write the Gibbs free energy G is equal to A plus PV. Gibbs free energy is mu times N. Gibbs free energy is 0 because there is no restriction for the number of photons in the cavity. So free energy is 0. So therefore we can write A is equal to minus PV. Okay. So A is equal to in terms of energy minus 1 by 3 U. Okay. So the one third of internal energy is the Helmholtz free energy. So we can write this thing as, but this internal energy U is a function of, so the remaining things are constant, 8 constant, pi raised to 5, k raised to 4, 15, h cube, c cube, all are constant. So we can write U is proportional to V t raised to 4, isn't it? So A is proportional, A is equal to okay, since U is proportional to V t raised to 4. Okay. Now we have the entropy. Entropy S is equal to, you can write U minus A divided by T, or U equal to A plus Ts. So from that U S equal to U minus A by T. So U minus A is one third of U divided by T. So this is equal to 2 by, actually minus A. So minus A is A itself is 1 by minus 1 by 3 U. So this will be 1 U plus 1 by 3 U. This is equal to 4 by 3 U divided by T. Okay. So S equal to 4 by 3 U divided by T. Therefore, S is proportional to, U is proportional to V T raised to 4. So divided by T. Okay. So this can be V T cube. So S is proportional to V T cube. Okay. But the specific heat specific heat capacity at constant volume. Cv is equal to, we have relation for T dou S by dou T is there. Cv is equal to constant volume, or you can write dou U by dou T. Both are right. Okay, at constant volume. So we can use this thing. T dou S by dou T. Dou S by dou T at a constant volume, which is equal to T dou S by dou T. So Cv is proportional to, we can write Cv is proportional to T into dou S by dou T is the constant volume is V T cube T. So proportionality constant comes here. So T square it will be. So this can be written as Cv is proportional to V T cube. Okay. So if the radiation undergoes a reversible process, if radiation undergoes a reversible adiabatic process or adiabatic change. For reversible adiabatic change, delta S is equal to 0. That means entropy is constant. Therefore, we can write this thing as Vt cube. Entropy is proportional to Vt cube. So Vt cube is constant. Okay. But we know that P is proportional to T raised to 4. Okay, PV is proportional to V T raised to 4. Okay, so P is proportional to T raised to 4. Therefore, P raised to 1 by 4 is proportional to T. Okay, substitute here in this thing. So in this expression, V T cube is V 3 by V T raised to, sorry, instead of T raised to 3, we can put P raised to 1 by 4 raised to 3. Okay, P raised to 3 by 4 is a constant. So for a reversible adiabatic process, V P raised to 3 by 4 is a constant. Or taking the taking power of this thing 4 by 3 exponent, we take the power of this thing P raised to, or V raised to 4 by 3 is V raised to 4 by 3 P is also another constant. Okay, so therefore we can write, or PV raised to 4 by 3 is a constant. P is, yeah, so we have PV raised to gamma is a constant. Okay, so here gamma is equal to Cp by Cv is equal to 4 by 3. So we got gamma of the radiation, that means photon, is 4 by 3, but for photons gamma is infinite. Actually this is not the case. So this is actually not in agreement with the actual case of photons. Okay, so we have derived the pressure PV, which is proportional to T raised to 4. So this is another form of Stefan's law. And radiant energy density per unit. So radiant energy per unit time per unit area is also proportional to T raised to 4, where sigma is called the Stefan constant. Then we have derived energy density. Energy density is also proportional to T raised to 4. Then next is we have obtained the value of S, the functional form of S, C we have, and gamma, which is obtained as the wrong value. We should get infinity, but we got 4 by 3 from this calculation. Okay. Okay, that's all for today. Thank you.